This experiment is called the neutralization challenge. What I'll do is read the entire procedure to you so you have a good idea of what's going on. I'll read it rather quickly. I'll add certain additional details when I think it's relevant, and then I'll show you some sample data, and this can help greatly when you come up with your own data. All right, ready? Let's begin. In this experiment, you'll be given a random amount of baking soda, and your goal is to precisely neutralize it. The goal for you is to discover how the mole is a great tool for mixing chemicals using just the right amounts. Remember, the mole is just a number, and it's easy to measure. This is all about the measuring part. Common acids and bases react to form a salt and water. For example, hydrochloric acid and sodium hydroxide form sodium chloride, there's your salt, and H2O, that's water. When equivalent amounts of a strong acid and a base react, the solution will become exactly neutral. That means it has a pH of 7. This can easily be confirmed using some pH paper. Very quick. If we use too much acid or too much base, the excess will remain and the solution will not be neutralized. How many grams of each should we mix? Well, that's the important part. We can calculate the precise amounts of reactants needed using the mole. It's all based on the idea, and here I am adding some additional stuff, that 1 gram of this is not the same as 1 gram of that. For example, in the above reaction, if we were to use 36.5 grams of HCl, which I purposely chose because it's exactly a mole, 6 times 10 to the 23rd molecules, hydrogen being 1 gram per mole, and chlorine being 35.5 grams per mole, we would need to use 40 grams, which is 1 mole of sodium hydroxide, 23 plus 16 plus 1, to neutralize it. Use too much NaOH and the solution will be basic. That'll turn the pH paper blue. Remember, blue equals basic. If we use too little, the solution remains acidic and the pH paper will be red. We need to get it so it's just right. We need to use a larger mass of sodium hydroxide. Note the 40 grams for the 36.5 grams in this example, because the mass of sodium hydroxide is a bit higher than the HCl molecule. Now, important note, that's not what you're going to be mixing. I'm giving you different acids. That was to serve as an example. For this experiment, you're going to be given some baking soda, that's sodium bicarbonate, as your base, and acetic acid. Think of that as vinegar, only much stronger, as your acid. For advanced students, you might recognize that if you mix those two things together, for reasons we don't need to go into here, that solution will not create an exactly pH 7 mixture. But your instructor has performed this reaction on an equimolar scale, doing it just right, and so your goal is to match the color of the pH paper to the one that he obtained. I hope that's clear. Do this and you receive full credit for the lab. That's how we're going to do it. Safety warning. Pure acetic acid smells, well, I wouldn't call it nasty, but I'd call it strong. It's 20 times stronger than vinegar, and it's 20 times smellier. So work near or in a hood if possible, and definitely work in a well-ventilated area. Here's your instructions. Working in groups of 2, you're going to receive a random amount of baking soda, also known as baking soda. Sodium bicarbonate, also known as baking soda. To determine how much acetic acid to use, fill out the table below and precisely neutralize your solution. Then bring it to your instructor for analysis. He'll stick some pH paper in it, and if it matches his color, you receive full credit and your approval stamp. Okay, so you're going to fill in this chart. For those of you who have persevered and have listened to this whole thing, I'm going to go ahead and give you some sample data that can help. Here's the molecular weights of each one. This is all designed to just give you some handy information. It turns out the mole ratios here are all 1 to 1 to 1 to 1, but if they weren't, it wouldn't matter because the molecular weight is just the molecular weight. For NaHCO3, 23 plus 1 plus 12 plus 48 equals 84. This totals up to 60 grams per mole. This one is not CH3CO2H, but it's the heavier sodium atom there. Technically, that would be a sodium ion. Water's 18, HOH, so 2 for the hydrogen, 16 for the oxygen, plus 44. Check that it's mass balanced. I see 144. 82 plus 18 is 100, plus 44 is 144. Check. Looks good. Now for the grams, all we'll do is for each group, we'll give you a little bit of random amount of sodium bicarbonate, that's baking soda, and it'll vary from group to group. So copying from another group won't work. To keep things simple, I did 0.05 moles, right? A tenth of a mole is 8.4 grams. Half of that is 4.2. Similarly here, 3.0, 4.1. Can you see how this is all based on 0.05 moles? If you see that, then you got it. That's all you do. It's a 1-to-1 ratio. We're going to mix. If I gave you 4.2 grams of baking soda, you're going to mix it with exactly 3 grams of acetic acid, and you will be good to go. In terms of moles, 0.05 across the board. That's some sample data if you were given 0.05 moles. If you're given a different amount, you'll be scaling differently. I hope that makes sense to you, and good luck with your experiment.